Hello, and welcome to a digital lecture for Calculus 2 at Salt Lake Community College. In this video, we're going to go through section 10.3, polar coordinates. Up to this point, we've talked about how to parametrize a curve in terms of how to change the variables into a function of t instead, and that will allow us to graph a plethora of functions, a plethora of curves anyway, that would not be defined as functions in the Cartesian plane. We also have what is called the polar coordinate system, which is something similar. We're still going to take our coordinates from Cartesian plane, so the rectangular x and y coordinates we're familiar with, and we're going to change that into something else. This is a system that was developed because sometimes rectangular systems and coordinates aren't really that intuitive, or they're not very that convenient to use. For example, here I have an example of both a rectangular and a polar coordinate system with the graphing of the same points. If you take point A, the way that I would get from that starting at the origin, I'd have to define both x and y axes, which is a little bit arbitrary in most cases. And then in order to get to A, which is defined as an x and a y coordinate, I would have to go in the x direction, and then I'll have to go in the y direction. So the x direction and then the y direction, that travel will get me to A. However, overall, that was unnecessary. What I really just need to do is go from my origin, and I need to find out what this straight line is, what that is to A. That takes some calculation, because then I would need to find this Pythagorean theorem. I'd need to find the hypotenuse here in order to find what that distance is. And then I'd have to also come up with an equation for that, because there's not an easy way in a rectangular system to say, hey, go this diagonal direction in order to get to your end point. The same is also true if I had this point of B. This would be defined in some x direction negatively and then some y direction negatively, and that gets me over to my point B. But again, what I really just need to do is say, start at this origin, face the direction that B is, and walk a certain distance away. If I did this with the polar system, what the polar system has is it has a single axis, sometimes just called the polar axis, and each point is not going to be defined in terms of an x and a y coordinate. What each point is going to be defined as is a r coordinate, which is going to be the radius, and a theta coordinate, which is going to define the angle measure of rotation. R here is the distance from this point to A. So right here, this is the distance r. And if you look at this, we have concentric circles here. You could also consider this distance r to be right here on that axis, on that rotational axis. So I could say, okay, go this certain distance, but also turn an angle measure defined by theta. Now I just have two coordinates that tell you exactly how to get there, and they don't waste time. Going in the x and y direction, if you add those two together, that's going to be more distance than necessary, whereas you could just take the distance r. Maybe you'll see x and y coordinate systems in stuff like streets that have like a rectangular system. For example, Salt Lake tends to be a more grid-like system. However, if you're in any other position, you simply just need to say, okay, what direction am I facing? What direction do I need to turn? And how far in that direction do I need to go? The same again applies for B. All I need to do is figure out, okay, how far do I need to travel? Maybe I'll do this one in purple. So how far do I need to travel? And how much of an angle measure do I need to spin in order to be facing in that direction? The other benefit of this is that we just have a singular axis, and if you notice, we tend to draw it just as a positive one, a positive radius axis for the polar axis itself. That way we don't need to arbitrarily choose x or y. We could just say, all right, the polar axis is the direction I'm facing. What direction do I need to turn? I don't need to think about x or y, which a lot of people try to align with something like the like east and west and north and south, something like the cardinal directions. With this, we could just say, what direction am I facing? What do I need to turn? So that's kind of the benefit of the polar coordinate system, and it was developed by Newton for the specific reason that rectangular coordinates are a little bit obtuse to actually physically use. Alright, so in this case, again, we're going to be using a coordinate pair of r and theta, where r is the distance traveled, or the radius sometimes, and theta is the angle of rotation from the polar coordinate axis, or just the polar axis. In order to convert back and forth between these, we actually have a set of equations from trig that help us with this. What I have here is a triangle that's already labeled out here, so a triangle with x distance and a y distance, and r being the radius here, and also theta as the angle measure between x and the radius there. And this can be used for any arbitrary x or y point and convert to r and theta. What we can use are the familiar equations from trig, for example, sine and cosine. Sine, wrong pen. Sine for this function, sine of theta would be defined as the opposite over the hypotenuse, or y over r. And then if I multiply r over, I get r sine theta equals y. And I can do the same thing for cosine to get r cosine of theta equals x, which are the first two equations that we have written here. This is helpful because now I've defined each coordinate, x and y, in terms of r and theta. This will be useful when I'm taking Cartesian equations and I'm trying to convert them into polar equations. I can replace any instance of y with r sine theta, and I can replace any instance of x with r cosine theta, and then try to get r by itself. We're typically looking for r equals a function of theta. Other equations that can help do the reverse, though, we know, again from this triangle, we know the Pythagorean theorem, which says that x squared plus y squared equals r squared. That's the third equation here. This, as well as tangent of theta, which is the only basic trig function we didn't use, would be defined as the opposite over the adjacent, or y over x. These two will also be used, but in the reverse way. Instead of going from a Cartesian coordinate or a Cartesian equation into a polar one, these can be used to change polar into Cartesian. Because now I can take r and I can define it as x's and y's, and I could take theta and define it as y's and x's by simply getting arctangent. So theta equals arctangent of y over x. But these four basic equations, which just come from simple trig, are going to be the ones that you would need to convert back and forth between points in Cartesian or polar coordinate planes, or equations in those planes. We're going to do a little bit of that. So I talk more about that again, saying that r cosine theta and r sine theta are typically used to convert Cartesian equations to polar, whereas the other two, which this should be an equals, which the other two are typically used to convert polar equations into Cartesian. And then if you're converting individual points, so like an x and y coordinate, then you're actually usually doing the opposite. Because if you have x and a y, then you can find theta. If you have an x and a y, you can find r. Now, in the next few examples, and most of what we're going to be doing in this video, is we're going to show how to graph polar equations and special types of them. So what I'm going to do with these ones is we're going to graph them, and then we're also going to convert it to its Cartesian equation equivalent. When graphing them, we may even be able to recognize if the equation is going to be correct or not. So the first two examples are both instances where I just have a single variable. Kind of like if I were to have x equals 2 or y equals -1. We recognize these as both horizontal and vertical lines. If I have r equals something or theta equals something, we need to know what this represents in a polar system. R equals theta. R equals theta means the radius is equal to 3 at all points or at all angle measures. So that means the radius at 3 would be here, and that's also true at this angle measure, and this angle measure, and this angle measure. We know that this is divided into 4 pieces per, so this is actually pi 6, and this is pi thirds, and this is pi halves. So you may need to brush up on trig if necessary. But the radius of 3 is going to be true at all points. Which means, as you see here, this will construct a circle. Or as good as a circle I can draw. If I try to convert that into its Cartesian Equation equivalent, again, the functions we're going to use is we have x squared plus y squared equals r squared, and we also have tangent of theta, or y over x equals tangent of theta. These are ones that we're going to use typically to convert polar into Cartesian. The way we're going to do that is we're going to take every instance of r and every instance of theta and replace with these functions that we see here. In this case, I just have r equals theta. So what I'm going to do is just take the square root of this, and I'm going to replace r with square root of x squared plus y squared. Then if I square both sides to get a function that, or equation that looks a lot more familiar, I get x squared plus y squared equals 9. This we should recognize as the definition of a circle with a radius of 3. You can also do this by squaring first and getting r squared equals 9, and then replacing r squared with x squared y squared to get directly to there. That's another way to do it, in a common way that we'll evaluate some functions in the future. The second one we have theta equals pi over 4. So this is not going to be the same thing. This is saying that the angle measure is pi over 4 for all of the other variable being the radius. So that means no matter what the radius is, we have that the angle measure is pi over 4. Well, pi over 4 is in quadrant 1. It's right in the middle between 0 and pi halves. Pi over 4 is around here. And I'm going to have, or 4, not 2. And I'm going to have that angle measure for all radii. So that means radius of 1, radius of 2, radius of 3, 4, 5, 6. Notice what this is making? It's making a straight line. Or, again, as straight as I can make it. However, this is not the entire graph, because we could also theoretically have a negative radius. What a negative radius is going to do is you find your angle measure and you go back from that direction. So we could also have negative radii here, which means that this line does continue all the way in both directions. Now, if we try to replace theta here, we have, from the previous equations, we have tangent of theta equals y over x. And the way we tend to use this is we say theta is equal to arctangent, or tangent inverse, of y over x. So that will allow us to take theta equals pi over 4 and replace theta with arctan of y over x equals pi over 4. Then again, I could take tangent of both sides and say y over x equals tangent of pi over 4. Tangent of pi over 4 is otherwise known as 1. So we have y over x equals 1, or y equals x, just as our simple equation. If you wanted to, for this particular case, since we just have theta equal to this, you can also just put pi fourths into theta, and you get directly to this. That also works. A couple different ways about it, but kind of get used to working with arctangent in this way. Looking at this equation we evaluated, though, y equals x, that makes sense. That's what this graph is as we're going up in the x direction, we're going equivalently in the y direction. So this is just a y equals x line. Okay, so circles and straight lines, that's what those look like. If you just do r equals something, that's going to be a circle of that radius. Theta equals something that's going to be a straight line going through that angle measure. Now, what if we introduce both variables, just r equals theta? Again, this is just like if you're taking algebra, we'd also introduce what y equals x looks like. So, likewise, we're going to do r equals theta. In order to think about this and a lot of the ones in the future, what we're going to do is just plug in values for r and think about what value we get for theta. And values we plug in for r are typically going to be the ones we're most familiar with. Stuff like 0, pi halves, pi, 3 pi over 2, and 2 pi. Well, in this case, though, if I plug in that radius, or sorry, these are my angle measures. If I plug in that angle measure, let's see what I get as a radius. So 0 into this, well, I get 0. Pi halves, pi, 3 pi over 2, and 2 pi. So now I have my points, and I'm just going to graph them. 0, 0, pi halves and pi halves. Pi halves is about 1.5-ish, so something around there. At pi, I have pi, which is a little bit over 3, so 1, 2, 3, right there. That's the angle measure pi, and I'm going in that direction. Then the angle measure of 3 pi over 2 is going down, and that's going 3 pi over 2, so that's about 4.6 or so. 1, 2, 3, 4, a little bit over 4. So somewhere in there. And then 2 pi is about 6.28, so something over here. And if you're ever unsure, again, you can always plot something else. For example, pi fourths, because I'm not exactly sure what's happening between 0.1 and 0.2. 3, 4, 5. But I'll just get pi fourths again, which means that at pi over 4, I'm going a distance of pi over 4, which is maybe right there. Well, it should be less than 1, actually. So something like that. That helps me identify that what this graph is doing, if I connect all these together, is it is creating a spiral, sometimes known as an Archimedean spiral. If we try to make this a graph, again, or a Cartesian equation, what we're going to do is take our two equations of x squared plus y squared equals r squared, and y over x equals tangent of theta, and we're going to try to isolate both of those. Well, r, we did that before. We can replace r equals theta. We can replace r with the square root of x squared plus y squared. And theta, like we did before, I can replace theta with arctangent of y over x. You can square both sides if you want to, but you get x squared plus y squared equals arctangent squared of y over x. Not a very pretty function, but that makes sense. Looking at this, this is not something that makes sense in most Cartesian functions. So we get something we can't really isolate either y or x. All right, so there's a couple examples of working with those. We have circles, straight lines, and spirals. If you were to multiply this by a constant, it just kind of expands faster or shorter, depending on what the constant is. And if you add a constant to this, it just kind of shifts it over. And you can experiment that if you so please. The next few examples we're going to do are more, I guess, interesting cases. Something that's some of these graphs that will make very familiar shapes that we're going to be able to identify just by looking at the equation itself. So let's talk about those. All right. Okay, so we have a few more examples here. In these examples, what we're going to do to plot these is we're going to make points for them. And so kind of like what you would do when you're first starting with algebra, just start plugging in points and trying to see what these do. These are going to make very particular shapes, but we'll talk about what these shapes are in just a moment. First, let's just explore with this. So what we're going to do is we're going to plug in values for theta and try to see what radii those will give me. Here we have r equals 2 minus 2 sine of theta. Now, I notice the main function here is sine of theta, and so what I'm going to use is familiar values for sine of theta. And because theta isn't adjusted by anything, which we'll have a few of those later on, we don't need to adjust our values, and what we could just use are the most familiar ones. So 0, pi halves, pi, 3 pi over 2, and 2 pi. This will also be true for the next problem, and most of the ones to come. We're going to try to use the most familiar values as necessary. These might be enough, they might not be enough. If there are bounds in terms of what theta is, then we'll use those. But otherwise, we're going to see how this goes, and if it doesn't seem to create or fill out the picture, we're going to keep going, or we hopefully should be able to figure it out by symmetries. If I try to find the radius, I plug in theta of 0. Sine of 0 is 0, so 2 minus 0 is 2. Then sine of pi halves. 2 minus 2 times sine of pi halves, where sine of pi halves is 1. That'll give you 2 minus 2 is 0. Then pi will also give you 0. This will kind of be like trig, where you're going to see a lot of repeated numbers, but you'll start to see positive and negatives showing. Because the next one we're going to get, 2 minus 2 times sine of 3 pi halves. Sine of 3 pi halves is negative 1. So this is actually 2 plus 2 will give you 4. And then 2 pi and 0 typically will give you the same thing. We have 2 minus 2 sine of 2 pi is also 0. So we get another 2 overall. Not too bad. We should be able to plot these rather well. So at an angle measure of theta, or at an angle measure of 0, we have a radius of 2. So this point right here. At an angle measure of pi halves, I have a radius of 0. So I'm at the origin. At an angle measure of pi, I have a radius of 2. So that means in that direction of pi, I'm going to go that direction. So don't think about this as going negative. It's not Cartesian. You're just going in the direction or the opposite direction. And then for 3 pi over 2, we have distance of 4. So 1, 2, 3, 4. And then we're back up to this point. All right, so far this kind of looks like a triangle. Not exactly sure. So again, what you can do is try to test some points. Maybe something like pi over 4. It's a familiar one. Or maybe because it's sine, you could be a little bit more sneaky about this and do something like pi over 6. I could do pi over 6 instead, because pi over 6, sine of pi over 6 will give me a rational number. It'll give me 1 over 2 instead of root 2 over 2 or 3 over 2. Sine of pi over 6 will give you 1/2. So you get 2 minus 2 times 1/2, which is 1. So you get a value of 1. So that means at pi over 6, which is this angle measure here, I have a radius of 1. If you test 5 pi over 6, you're going to get the same thing. And so what you find is that this graph looks something like this. Again, to the best of my artistic ability. I'm not the best drawer. Kind of looks like a heart, doesn't it? That's what a lot of these will do. However, the next one's going to be a little bit different. It's not necessarily going to make a heart. It'll be a little bit more interesting than that. The next one, we have 1 plus 2 cosine of theta. And again, we are going to be able to use our same familiar values, and we just plug those in. 1 plus 2 cosine of 0. Cosine of 0 is 1. So that's 1 plus 2 is 3. Cosine of pi halves is 0. So that's 1 plus 0 is 1. 1 plus cosine of pi is negative 1, so that's 1 minus 2 is negative 1. Cosine of 3 pi over 2 is 0, so that's 1 plus 0 again, equals 1. And then 2 pi is going to give me another positive 1, an overall value of 3. So let's see what these do. So at an angle measure of 0, or 0 radians, I have a distance of 3. So right there. At an angle measure of pi over 2, I have a distance of 1, which is right there. At an angle measure of pi, so that's pi over 2, at an angle measure of pi, I have a distance of negative 1. What that means is I'm facing this direction, but negative 1 means you go backwards. So backwards from the origin will give me that point right here. So if I start labeling these in terms of the order that I constructed them, we have point 1, 2, 3, 4, 5. So I got this point to this point to this point. And then the fourth point will give me 3 pi over 2, which is down here. I'm going a distance of 1. And then I'm back to where I started. So this looks kind of weird. It looked like the previous one, but this point is more inside. Well, if I were to try to solve this, that's another way that you can try to evaluate these. You can try to maybe see where the radius is 0 in terms of like where am I hitting this origin here, because it looks like I should be, or you can also again test points, but this is an alternate way. you could say, all right, well, where does the radius equal 0? So 0 equals 1 plus 2 cosine of theta, if it does at all. Sometimes it doesn't. But this one should, because we notice if you subtract 1 and then divide by 2, you get negative 1/2 is cosine of theta. And that happens when theta is equal to, that would be in quadrant 2 and 3, and it's negative 1/2, so that should be 2 pi thirds and 4 pi thirds. Again, this is from the unit circle. So that means that 2 pi thirds and 4 pi thirds, I have a radius of 0. So what that implies when I draw this is that when I'm going from 1 to 2, I'm going to try to keep a smooth motion. I then am hitting this origin here before I get to 2 pi over 3, or as I approach it. Then I should be going in the direction of my third point. After that, I'm also should be coming back this way, going through 4 and hitting back to where I started. So this is like the previous one, except now I have an inside loop here. And again, you can test points in there as well. If you're plugging 2 pi thirds into this, you get 0. But yeah, there's a lot of other points you can check if you want to. For example, you can also check this one here. This would be 5 pi 6. So if we do 5 pi over 6 with this, I get 1 plus 2 times 5 pi over 6. That'll give you negative root 3 over 2. So that's 1 minus root 3, which, not sure off the top of my head exactly the answer for that, but it's a negative number. 1 minus root 3 is negative, which means that at 5 pi over 6, I am going a negative direction of some sort. It should be negative. It should be between 0 and 1. Okay, so these kinds of graphs have special names. If you look at the equations we worked with, they are relatively similar. They both have a constant plus or minus some amount of sine or cosine. These functions are going to be commonly known as limacons. It's definitely, typically should be limaçon, I think is how it would be pronounced in French. But in the United States, we just more colloquially call it a limacon. And again, they form from the equation a plus or minus b sine or a plus or minus b cosine. The value for a and b will determine the shape of it, as if we noticed before, we had different values. For example, 4, we had a and b both being 2, and we had this perfect heart shape. But in the second example, we had a, which was 1, is smaller than b, and we ended up with this inside curl. Furthermore, before I go to those examples, if we notice sine here, that means that the larger part of the graph I draw here is going to be on the y-axis, or what would be the y-axis is what we're familiar with sine. And since we have cosine here, the bigger part of the graph is on the x-axis, or what we would be familiar with the x-axis. So it's another thing that you can pay attention to. Overall, I have this here that kind of breaks down the different types of graphs you can get. If you have absolute value of a equals absolute value of b, again, not basically noticing the plus or minus, that's just going to indicate the direction of it, we have what is called a cardioid, which is what we graphed the first time. It's something like a heart. This one here, I believe, would be 2 plus 2 cosine here. If you have a is less than b, which is what we had in the second example, again, not considering their positive or negative versions, we have an inside loop. These are the most common too, but you could also have other versions of a and b. If you have a over b, the ratio of them is between 1 and 2. Before we had a was 1 and b was 2, so that would be 1/2. This would not be true. So if this ratio is between 1 and 2, then you have what is called a dimpled limacon. Basically saying that it's kind of like a deflated basketball, more or less. is you have this circle shape, but you have a more flat region. You would see this kind of stuff for engineers. You'd see this kind of stuff in a rotary engine. A rotary engine actually uses a dimpled limacon as the inside shape of it. If you think about the inside triangle that would be rotating around and trying to capture gases. So for those that know what a rotary engine is, that's an application of limacons. If A over B is greater than or equal to 2, you get more of a convex-like limacon. Basically, it looks like a circle, but not quite. It's not flat on any side, it's rounded, but it's not a perfect circle. Notice this one goes a distance of 4 from the origin, whereas if I go the other distance, I only have a distance of 2. Even though it does still look like a limacon or a circle, it's a little bit off. Now, you don't necessarily need to memorize these, but these are going to be very helpful so that when you look at a graph, you can just notice A and B, and you should have an idea of what the graph looks like. And then if you look at either sine or cosine, you then also have an idea of the direction of it, if it's going left or right, or if it's going up and down. So these can be very useful to evaluate equations and be able to look at something and say, hey, that looks familiar. That looks like something I should be used to. All right. Now we have a few more types of graphs we want to talk about here. First, we have what is called a lemniscate. So this one I'm introducing first. So a lemniscate. It's derived from the word of lemniscatus, which means adorned with ribbons. It essentially is going to look like an infinity sign, and we're going to show that here. We have r squared equals 16 cosine of 2 theta. Well, in order to get this to be something that's a little bit more usable, particularly if we're going to evaluate r, we can get r by itself by taking the square root of both sides. The square root of 16 is 4, and then we have times the square root of cosine of 2 theta. All right. Now, if we were to try to use our original equations, watch what would happen here. So don't write these down, just watch what would happen. 3 pi over 2 and 2 pi. If we use these original values, we plug in 0 into cosine. We get cosine of 0 is 1 times 4 is 4. We plug in pi over 2 into cosine. We get cosine of pi, which is negative 1, so that's undefined because it's under a square root. If we plug in pi, we get cosine of 2 pi, which is 1 times 4 is 4. Undefined 4. We just keep getting these values, so these aren't really helpful. The reason is because we notice now on the inside it's more complex than just theta. It's 2 theta. What that means in terms of trying to generate values for theta, instead of using these, what we're going to do is take the normal values. So take the normal values of 0, pi halves, pi, 3 pi halves, and 2 pi, and divide them by 2. That 2, highlighter, that 2 coming from the equation itself. If that was cosine of 3 theta, I would try to divide by 3. The reason is that way I can then take those new angle measures, plug those in, and we would get the answers that we would normally have for 0, pi halves, pi, 3 pi halves, and 2 pi. So let's try doing that instead. See where that gets me. So 0 divided by 0 is 0. Pi halves divided, 0 divided by 2 is 0. Pi halves divided by 2 will give you pi fourths. Pi divided by 2 will give you pi halves. 3 pi halves divided by 2 will give you 3 pi fourths. And 2 pi divided by 2 will give you pi. We already did cosine of 0, but now we could try these other ones. We also technically did pi halves as well. We found that to be undefined. If we do pi fourths into here, cosine of 2 pi times pi fourths, so that would be cosine of pi halves, is 0. 4 times root 0 is 0. So we get something we can work with a little bit better. If we do 3 pi fourths, cosine of 3 pi fourths will be cosine of 3 pi halves, which is also 0. times 4 is 0. And then pi will give you cosine of 2 pi times 4 is 4. So a little bit better. However, still a little bit unclear. Let's see what we have here. So we have, at an angle measure of 0, we have a distance of 4. And then we have an angle measure of pi fourths, which is right here. Maybe I'll do that in purple. So at that angle measure, we have a distance, a radius of 0. Which means that basically as I start approaching that angle measure, I should have my radius get smaller and smaller and smaller. At pi halves, it's undefined, so we'll see what we do with that. But at 3 pi fourths, which is right here, well, in purple. At 3 pi fourths, I also have a radius of 0, going to pi over 4, which has a radius of 4. So 1, 2, 3, 4. Right there. Something like that. Alright, this graph does not necessarily look complete, so we can try testing more of them. For example, looking at this pattern, these are all increasing by pi over 4 every time. So maybe let's do another pi over 4. If I do 5 pi over 4 next, I would plug that into cosine of 2 theta. 2 times 5 pi over 4 is 5 pi halves, which is equivalent to pi halves, which is 0. Cosine of pi halves is 0. So that's also going to give me 0. That means that that angle measure at 5 pi over 4, I get another radius of 0, which means that as I start approaching that angle measure, the radius should get smaller and smaller. It's going from a radius of 4 to a radius of 0. And if you continue this and do the next one, you'd also find that the rest of this region would continue like this. And therefore we have our graph. The purple lines notwithstanding, don't necessarily need those there. That was more for the construction. This would be what we call Lemniscate. As I said, it should make an infinity symbol. If you try to test anything between basically where it got to 0 and undefined, so between pi fourths and pi halves, if you're like, well, okay, well, what's going on there? If you try to test one of those, between pi fourths and pi halves, for example, is pi thirds, cosine of 2 pi thirds is negative. So you get a negative square root. Basically, anything between an angle measure of pi fourths and 3 pi fourths is going to be undefined. There's nothing here. And same thing between these regions, because you're going to get a square root of 0, or a negative number. So that's why we get no graph in those regions. That is how you'd build a Lemniscate. They tend to make this general form that we see here. Overall, it looks like either r squared equals a squared times cosine of 2 theta, and yes, 2 is very specific, or r squared equals a squared sine of 2 theta. We showed how to do cosine of 2 theta, and if you were to just make this a different number than 16, it would either just shrink the Lemniscate, or it would expand it, make it wider. R squared equals a squared sine of 2 theta is going to look similar to this. It's just going to be slanted. So you'll get an infinity symbol that looks more like this. So it should be on its side. Something like that. And you can explore that if you so please. Just test some number for a and see if you can figure that one out. These graphs, though, Lemniscates, are really just a special variation of another type of graph. Something that is a lot more common, and that is what is called a rose. A rose is a curve that looks like a rose. It looks like a flower. It's going to have multiple petals. Kind of like this graph here. We had a single petal of a flower and another petal on the other side. So this is like a two-petaled flower. However, flowers don't tend to look like this. They tend to be more symmetric. And there's a lot of math analyzing flowers and the amounts of petals you can have, for example, too. The equations for roses we're going to work with are all going to look kind of like that, except without the squared. We have r equals a cosine of n theta and r equals a sine of n theta. Notice that the value in front of theta can be different. It can be a different number. The ones that we're going to work with are all going to be natural numbers, so they're all going to be whole numbers. Typically positive. I guess you could say that they're integers instead. But they're most often going to be positive. So like a positive 2, a positive 8, a positive 7. And that value of n is going to tell you how many petals in the graph you're going to have. We're going to show a couple examples of this. But overall, if n is odd, so if you have sine of 3 theta, for example, or 5 theta, or 7 theta, then you're going to get that many petals. So sine of 7 theta has 7 petals because it has 7 there. If this was, instead of 7, it was 11 theta, then it would have 11 petals. If it's an odd number, you're going to have that many petals. However, if n is even, then you're going to have rows of twice that many petals. Meaning that if you have sine of, say, 4 theta, then you're going to have 8 petals. If you have sine of 10 theta, then you're going to have a flower with 20 petals, with a lot. If you think about this more, that actually means that it's impossible to have something like anything with 6 petals in it. The reason is because that's if we look at what 6 is, that would result from either one of two things. You either have that 6 here, which if this is a 6, then that actually means that you get 12 petals. Or you would have half of that. Half of 6 is 3. But if you had sine of 3 theta, then you wouldn't have 6 petals, you have 3 petals. So it's actually impossible to get something like that. To get something that's double an odd number. So 6 is not possible, 12 is not possible, things like that. Okay. Lastly, like we talked about before, we are going to adjust the angle measures that we work with. But also, as you work more with this, you should be able to identify where those petals are going to be. For cosine, cosine is going to have a petal basically anywhere that you have a multiple of pi. So because we know that cosine of, say, 0 or pi or 2 pi or 3 pi are all going to result in whole numbers, whereas pi halves and 3 pi halves and 5 pi halves are all going to result in 0. If we extrapolate on that, and then we already divide by what the middle is, so instead of like just pi times k, where k is an integer, you have pi times k divided by what n is, that's going to tell you where every petal is going to be. And at sine, it would be normally where pi halves is plus pi k, but then you divide that by n, and you get that you're going to have petals everywhere where that happens. Overall, it's going to typically be where cosine and sine would normally equal 1 or negative 1. However, we're not necessarily going to use this too much. This is just kind of a point that you can notice. We're still going to graph this the old-fashioned way by plugging in values, but smart values, and try to see what this looks like. And we're also going to keep in mind that symmetry is a thing, and that this should create a closed image. So if we basically don't return back to where we started, we can always continue it or finish it off or plug in more points. So let's do an example of that. We have r equals 4 cosine of 2 theta. Like before, instead of using 0 to 2 pi like we normally would, what I'm going to use is all those cut in half, so 0 up to pi. Instead of pi halves, we use pi fourths. Instead of pi we have pi halves. Instead of 3 pi halves, we have 3 pi fourths. Just like we did with the example of the Lemniscate. We divided all the normal values by 2. Furthermore, looking at that, because this is a 2, what we expect, since that's an even number, we expect double that. We expect 4 petals in this graph. That's going to be a very important key because that can tell us how much this graph is finished based on these original values. This might not be enough for the entire graph, but we'll see. If I plug in 0 into here, cosine of 0 is 1 times 4 is 4. Pi fourths into here, cosine of pi halves would be 0 times 4 is 0. Pi halves, cosine of pi halves times 2 is pi. That's negative 1 times 4 is negative 4. 3 pi fourths into that will give you cosine of 3 pi halves, which is 0 times 4. And then pi will give you cosine of 2 pi, which is 1 times 4 is 4. Again, for those familiar with trig, note that because we did that division, we get the numbers that we should be familiar with from cosine, or at least multiply by 4. We know that cosine starts with 1, 0, negative 1, 0, 1, and continues in that fashion. We'll go 0, negative 1, 0, 1, 0, negative 1. It would continue in that fashion. That's why it's really useful to divide these by 2 so you get that pattern to show up again. Sine would start at 0, 1, 0, negative 1, 0, 1, etc. But let's graph these. So at angle measure of 0, we have a radius of 4, so that'd be here. At angle measure of pi fourths, we have a angle measure or a radius of 0, which means kind of like the Lemniscate, we're going to curve in as we approach pi fourths. But now, unlike the Lemniscate, when we get to pi halves, we do get a value. Remember, pi halves is up here, but because r is negative, that means we go down from that. We go in the opposite direction of that angle measure, and we get 1, 2, 3, 4. So that means if I continue this curve in that direction, it's curving back down this way. And then at 3 pi fourths, which would be here, I get a radius of 0, which means we're coming back to the origin here. So we're coming back this way. Notice how that is creating a pedal. And then at pi, we have a distance of 4. Pi is right here, so we have a distance of positive 4. 0, 1, 2, 3, 4. So we go in that angle measure direction, a distance of 4. Now this graph isn't finished, particularly with what we know for the pedals, and you can continue to work with this. For example, we can continue to plug in points, say 5 pi fourths, and then 3 pi halves, and we know from cosine this pattern is going to continue. From 4, I'm going to get another 0, followed by a negative 4, followed by a 0 and a 4 if I do the rest. So 7 pi fourths and 2 pi. Just adding pi fourths every time. So that means at 5 pi fourths, which is right here, I have a radius of 0, which means I come back this way again, back to the origin. At 3 pi halves, I have negative 4, so 3 pi halves, I go back a distance of 4. 1, 2, 3, 4. So that means, if you notice this is making a nice smooth curve, I could theoretically just draw this out without lifting my pen at all. And then I'm going to curve back here when I get to 7 pi over 4, just right there. Whoop, purple. And then after curving here, I logically come back this way with 2 pi, and we complete our entire graph. Again, we expected 4 pedals, we got 4 pedals. This looks good. However, we didn't necessarily need to do this stuff. Because we knew how many pedals there would be and the graph we had constructed, we should have been able to use symmetry, basically just flip the graph, and be able to get everything else. So use your logic, use your symmetry, and you can construct these a lot faster. Let's do a couple more of these. Next one I have is 3 sine of 5 theta. Again, first thing we look at is that 5, that's going to influence both the angle measures we plug in and how many pedals we expect. Since 5 is odd, we expect exactly that many pedals. 5 pedals. Likewise, what we're going to do for the angle measures, we're going to take our familiar values, these typical values, and we're going to divide each of these by 5. that'll give us our new theta values. 0 divided by 5 is 0. Pi halves divided by 5 is pi tenths. That'll be a weird one. Pi divided by 5. 3 pi halves divided by 5 is 3 pi tenths. And then 2 pi over 5. What's weird about this is 2 pi over 5, that doesn't even get to pi halves. That's less than 1/2. 2/5 is less than 1/2. So all of these are going to be angle measures that are somewhere in quadrant 1. But we'll get to that in a moment. Now if we plug these in, you can use your knowledge of sine, or you can do them directly. Sine of 0 is 0 times 3 is still 0. Sine of 5 times pi over 10 will give you pi halves. This is why we did that. Sine of pi halves is 1 times 3. Pi fifths times 5 is pi. Sine of pi is 0. 3 pi tenths times 5 is 3 pi halves. Sine of 3 pi halves is -1, so you get -3, followed by 0. Again, you can use your logic of sine if you know sine pretty well, and just say, all right, well, this is following the 0, 1, 0, -1, 0, 1, 0, -1 pattern, and just fill these out by multiplying by 3. But now let's see if we can graph some of these. Again, this is likely not going to make the entire graph like last time, but hopefully we can start to figure out what the rest of this looks like. Maybe we might need to plug in a couple things. So 0, 0 is here, is where we start. So unlike before, we're not starting out, we're starting in. And then we go to pi tenths, which if we think about these in terms of tenths, well, can we really? Not necessarily. This is pi 6, this is pi thirds. Pi tenths would be below that, and pi fifths would be probably around here. So pi tenths, I don't know, let's say pi tenths is around here-ish. It's pretty shallow of an angle measure. We go a distance of 3. So something like that. Then when we approach pi fifths, which I'm going to say is right there, maybe we'll do that in purple again. Pi fifths should be somewhere between pi thirds and pi 6, closer to pi 6. That means when I start approaching pi fifths, I should start getting back to 0 because we have a value of 0. Then at 3 pi tenths, which is a little bit further from that, so I'm going to say here and maybe another here-ish. 3 pi tenths is kind of close to pi thirds. It's a little bit less. So maybe around here-ish. I have a distance of -3. So 1, 2, 3. I'm going to put that point here. And then I return at 2 pi fifths, which is almost pi halves, back there. Now we have 2 petals so far, but we should be able to continue this and create the rest. So all of these, if we notice, increase by pi tenths every time. 0 pi tenths, 2 pi tenths, 3 pi tenths, 4 pi tenths. Then we have 5 pi tenths, otherwise known as pi halves. That's awesome. 5 pi tenths into here, or we'll give you 5 pi halves, which is equivalent to pi halves. I'll give you 1 times 3 is 3. We get that same pattern again. So that means at pi halves, we actually have a distance of 1, 2, 3. So now we're getting more information about what's happening up here. And then we know we should be decreasing back. Looking at this, we can probably get the rest of this by just kind of doing symmetry. I could just flip it across the y-axis, or what would be the y-axis, for example. And what I should get is another curve that goes somewhere down here. That should give me another petal. And I should get one last petal over in this direction. Specifically, this would follow in this way. Let's see if I can do another color, maybe green to complement. So, maybe bigger. There we go. So I went that way first, then this way. Follow my pen down this direction, that way. Follow back up here, down this way. Back up here, and back down. Basically just what would make the most sense when writing my pen. It should just stay in nice fluid motion, so out, in, out, in, out, in, out, in, out, in, out, back in. So those are a couple examples of these rose curves. You can also notice, by the way, that these are all fitting inside of a circle defined by what the value of A is here. So it's a value of 3. It should be residing inside of a circle of radius 3. Likewise, the previous one had a value of 4, so we're sitting in a circle of radius 4. Okay. Almost done. We have one more example and another way of dealing with it. It kind of has to deal with how I was looking at these a lot of the time. If you notice, I was drawing stuff like pi 6, and in the previous one, I was drawing all of the ones like pi fourths, 3 pi fourths, 5 pi fourths, 7 pi fourths. These are all the values where we have a value of r to be 0. These, if you notice, the function is getting closer and closer to that. At that point, when I reach this origin here, this function here looks like what we call a tangent line. And tangent lines are another way of trying to evaluate polar coordinates. Evaluate where the tangent lines are, and then you can evaluate the curve in another way. To understand that, what we first talk about is how to take a derivative of polar coordinates. Kind of like what we did with parametric equations. We define that as dy over d theta over dx over d theta. So instead of dy over dt divided by dx over dt, we just have thetas instead of t. And if we think about x and y being the equations from the first page, if we think about x equals r cosine and y equals r sine of theta, when we take the derivative of those with respect to theta, we have a product rule. So that means we would do, for the top, for dy d theta, we'd have the first times the derivative of the second, which gives you r cosine, times the second times the derivative of the first, which is whatever derivative of r is, times sine. And you get the same thing on the bottom, just negative, because the derivative of cosine is negative sine. So this would be the derivative of an arbitrary equation defined as r equals some function of theta. This is how you could find the first derivative. Now, if what we can do with these is now consider what the numerator is. If the numerator ever equals 0, that means you have a horizontal tangent line. And if you have the denominator equal to 0, so the top equal to 0 implies horizontal tangent. If you have the bottom equal to 0, that would be undefined typically, but that actually means that it's a vertical tangent line at that point. So you can use those pretty handily as well. However, in what we were just working with roses, we know the tangent lines are going to show up where r equals 0. Which means if we think about that, if we plug in r as 0, these pieces cancel. You just have dr d theta times sine of whatever the angle measure is over dr d theta times cosine, and sine over cosine is just tangent. So that means at that point of r equals 0, you have that the derivative is just tangent of theta. And what that means is that all we really need to do overall to find those tangent lines is simply plug in r of theta into our original equation. That would find our tangent lines. And by the way, this here, us getting tangent of theta as a result, this is why these things are called tangent lines. And why it's connected or it's linked to that specific other function in mathematics. So those are a couple ways of finding horizontal and vertical tangents. But for roses, like the one we have here, we can calculate this by instead just finding where it equals 0. Wherever it equals 0, that's going to be our answer. Or that's going to be our tangent lines, and we could draw the petals within that. So instead of plugging in points, what I'm going to do is set r equal to 0. So 0 equals 5 cosine of 4 theta. Well, that's pretty easy. 0 equals cosine of 4 theta, just dividing by 5. And then if I take cosine inverse of both sides, cosine is equal to 0 at many places. It is explicitly equal to 0 at pi times k, where k is an integer. So something like 1 or 2 or 3 or -1 or -2. Or 0, really. So 0, pi, 2 pi, 3 pi, 4 pi, 6 pi, etc. Those are all places where cosine... sorry, not cos. That'd be for sine. Cosine is equal to 0 at pi halves. Sorry. So pi halves plus pi k. That's where cosine equals 0. It equals 0 at pi halves, 3 pi halves, 5 pi halves, 7 pi halves, etc. Then, if we get theta by itself, by dividing by 4, we get that theta is going to equal pi over 8, that's pi halves divided by 4, plus pi fourths times k. So times some multiple of pi fourths. That will define all of our tangent lines. So pi eighths, that's, if pi fourths is right here, pi eighths is half of that. So around here, that is going to define a tangent line. I'm going to draw a full line there. If I add pi fourths to that, that'll give me 3 pi eighths, which is, again, between pi fourths and pi halves, so somewhere right here, maybe. So bad drawing these straight lines. Something like that. That would be pi fourths. That'd be 3 pi eighths and pi eighths. If we add another pi eighths to this, or pi fourths, so we have pi eighths so far. If we add pi fourths, we add 3 pi eighths. If we add another pi fourths, we get 5 pi eighths. That'll be equivalent distance, somewhere around here, maybe. Something like that. Five pi eighths. And then we add another pi fourths. That's another 2 pi eighths. We get 7 pi eighths. 7 pi eighths would look something like this. If I continued like this, 7 pi eighths plus another pi fourths, or 2 pi eighths, would give me 9 pi eighths, which is right here. We already drew that one. That's why I drew pi eighths going all the way down. So we have all of our tangent lines in place, and all we're going to do to graph this is put our pedals in between here. Since the radius is 5, I know that each pedal goes a distance of 5, so 5 there. There should be a pedal in the middle there, a pedal here, a pedal here, 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 and here. So it's going to look like that. So pedal there, pedal there, pedal there, pedal there. And I just finished the rest of this off. If we also check the equation itself, because we know we had 4 theta, that implies we have 4 times 2 equals 8 pedals, which looks like we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 pedals. So that is another way of graphing these equations. You could do this for other things as well, like limicons. However, you'd have to find both horizontal and vertical tangent lines, and that basically just bounds where the limicon is. So if you think about a limicon like this, it's just going to find where it equals 0 horizontally and where it equals 0 vertically. So it's going to bound those. This is really useful for roses. So another way of applying and dealing with that without really plugging in values into the original equation. Okay, with that said though, I know this was a long video. There's a lot of stuff to cover here, a lot of examples. But if you have any questions, feel free to put those in the comments below, or ask your instructor directly. With that said, I hope you have a nice day.